Just use the down arrow on the.
Ah.
Oh, there we go.
Yeah, okay. So, yeah, read that. So this study started life essentially as an endeavour to refute stuff in the literature that was saying mathematicians, and source says, insist on giving exams to their students and teaching in traditional ways, with direct instruction, all this uploaded stuff. As it went along and more of us joined the project team, the scope of the project's also expanded, and I guess so now that's certainly still an objective. Also, we've got this amazing, I guess, oral history collection. We've done about 40 interviews, and people are doing really amazing work in maths education, and we've sort of got this living record of all different things that are going on that aren't necessarily being reported. And the third thing is looking at, this is a quote from one of the people in one of the lectures. So starting, thinking about what are we trying to do when we teach maths and stats, and how do we justify our existence? If there's a common public perception that maths is all about learning how to fill in your tax return and so on and so on. And computers can do that now. So what's the story behind what we're doing? So the official title is Educators' Views on the Teaching and Learning of Maths, Stats and Numeracy, or something like that. Structured interviews, 3 basic questions: what should students gain, how should they be taught, and how should they be assessed? That's the project team down the bottom. So as Don said, what we're talking about today is we're just going to report one single result and one observation arising from that result. So we looked at the data on what should students gain, and we did a thematic analysis on it, and it was very cool because it all worked according to what the theory says it should. So not everybody who's been interviewed made it into this data set, just because it takes an eternity to process the interviews. And it was just, there was a desire to actually do something and say something, to see if this whole methodology was going to work. So these are the people who are included in this particular thing. I guess the other thing to note is the balance. So we had 10 people who sort of teaching folks who teach both maths and stats, 18 people who only teach maths, and 5 people who only teach stats.
And the other thing, I guess, about this, that the interviews, we've gone to people who have an interest in maths education and an interest in developing it. So we haven't been talking to research mathematicians unless they also have an interest in teaching.
No, we've only talked to practitioners.
Yeah, and we haven't talked
not theoreticians.
To education people who know a lot of theory about education, but not necessarily much maths. So it's essentially the practical things. And if any of you would like to join the study, we're happy to talk to you and interview you at your leisure.
Yeah, and the results are it's a to die for data set. It's so rich. It's just marvellous. So, the thematic analysis actually worked a treat, and everything converged just like it was meant to, and all the rest of it. Essentially, the deal was each line of which person said got coded according to what we thought they were saying. That was an iterative process, because as new people kept coming up, someone would say something explicitly and you go, oh, yeah, actually 3 other people said something like that, but I didn't pick up on it before. So you sort of went around in circles for a while. But after about 14 or 15 interviews, the code stabilised and everyone else was fitted into that. So that's meant to happen. So that was good. And then we looked at all the codes and sort of grouped them into classes of big ideas. And this is what we ended up with. So four main themes of concept mastery, which had two subsections, one the technical mastery and one the understanding, mathematical thinking, communication and appreciation. Do you want to talk next on? No?
Okay, so the idea of content mastery.
We just want to define.
We just want to define each of these terms. So.
And the definitions came from the interviews. We can back them up by literature, but what we've got is just sort of the set of tags that were clumped together and we labelled content mastery.
Yeah, and in a lot of cases, a lot of people see the technical mastery as leading to the conceptual understanding. So in a lot of cases, there's focus on technical mastery with the hope that conceptual understanding will come from it, not necessarily explicitly being taught. But most of these, I should also say, most of these interviews are first year lecturers, although there's a few who were teaching higher courses, higher levels. Mathematical thinking. I mean, that's quite a difficult thing to actually define. What is mathematical thinking? As you were saying, what's a story? So these were the kind of ideas that were coming out. I think one of the things that we found was that we tend to teach mathematical thought.
Hey.
Maybe not mathematical thinking, and I'll leave that idea just hanging there for people to think what the difference might be. But this was, the idea of higher order thinking, being able to problem solve, critiquing solutions, those kind of things that we were talking about in our last talk about what we did with first year engineering students. Communication, there's essentially two aspects to communication. Receptive, meaning understanding other people's maths, being able to read mathematics, and also expressive language, being able to express the mathematics to, say, to tell somebody else to write your reports. And multiple formats for communication, written, spoken, graphical, demonstration of mathematical ideas. And then mathematical appreciation, which is possibly the most airy-fairy one of all. What is mathematical appreciation? Well, understanding the relevance of mathematics, understanding where it comes from in history. And I think that also includes understanding things like indigenous mathematics and other forms of mathematics. The interconnectedness between mathematical topics, which I think a lot of high school tends to not teach and tends to silo topics. So trying to undo that, and just the beauty and interest in mathematics as an art form.
Yeah, we also, so those four themes, so mathematical thinking, mathematical communication, content mastery and appreciation, they were consistent across the board. So they were consistent for stats people, for maths people, for both the surfacing subjects, for first year subjects, for higher subjects. Everyone wanted that package basically. There were a few other more localised things, localised meaning a particular subset of the cohort sort of spoke to these ones. So some first year academics thought that changing students' mindsets from school mindsets was important. Most of our statisticians thought that developing appropriate workplace skills was very important, even in the first years. And some first years and the people working in support also thought that developing self-confidence and self-efficacy in students was important, but we're not talking about those ones now. We just want to talk about those four global themes. Okay, so that was the results that we came up with, these four pretty clear sort of major themes that everyone agreed on, and they make sense, and they're highly consistent with what the literature says is important as well.
Yeah, I think there's probably nothing here that everybody wouldn't have been thinking themselves anyway, but we now have a body of evidence and a large database of evidence that supports what we all think, which I think is probably also an important consideration.
And so we wanted to make one observation from this Laura, you've got a question.
I was amazed when reading all the interviews about how consistent all the math educators were, and it was obvious to them that we want these 4 things, and the disconnect it has with what management, for example, the people who don't do math think what math is supposed to be. I think it was the unanimity inside the community and how misunderstood we are outside was just shocking to me.
Thanks, Laura.
Thanks.
Okay, so our observation is in linking these goals that we have to what people reported as their practice. And so content mastery, it's kind of obvious that we explicitly teach that. Like Don said, a lot of people, and there's, it's not unanimous by any stretch, but, you know, the large body of people hold the view that you teach them the technical stuff, learn to turn the handle, and through that they can go on to understand understand the bigger picture. Some people, especially the statistics community, argued the opposite direction, that you teach them the big picture and then you get your hands dirty in the details later. But regardless, you know, the whole point of doing a course is to learn the course content, so we teach that. Mathematical communication was very important to very, very many people, and it is taught explicitly in very many cases. It was interesting to me just how many people said that they would be doing oral assessments if they had half a chance, because they think they're better, but also because they're a great assessment of communication, which is an essential part of maths. A lot of people said that. So these two are, in general, being explicitly taught in our courses. Okay. For the other two, this is where we see a distinction between what the stats education community and the maths education community are doing. And I'm generalising of necessity. I can point to exceptions in both, but in general, what we're finding is that stats education has sort of moved to a focus where people either are or wish to be presenting the big picture, the story first, and letting the computers take care of the details. And there's quite an explicit focus on the thinking. How do you take this real world thing and turn it into a story and get numbers to support that story, and then turn it back into something palatable for your reader? And that also feeds into the idea of mathematical appreciation by appreciating the utility and the power of the statistics and its relevance in the real world. So, Nazim, you can disagree if you want or agree if you want. I think you're a representative statistician. Oh, sorry, Joe, I missed you, Joe. Okay, on the other hand, in maths, these were generally not explicitly addressed. They came up time and again as goals. Students would pick these things up, but people didn't say, and when I'm teaching, I do blah, so that they'll learn mathematical thinking well. So, you know, people, in fact, sort of often the opposite comment was the case. One interviewee said, I wish they came in with mathematical thinking because it's very hard to teach in a university environment. And other people say, well, I want them to gain mathematical thinking, or I want them to gain an appreciation of the mathematics, but presumably by osmosis or from some other subject or from somewhere else. It's not explicitly built in.
I think in a lot of cases, the time constraint was something that was mentioned, that, you know, we've got to get through this huge body of work within the time period. So we don't have time to teach any of this other nice stuff that we'd like to do.
That was, I mean, everyone's pressed for time. Courses are crammed with lots of things. Like Don was saying, earlier, and I think it was Skemp who first wrote about this in the 60s, 70s. Anyway, psychology. So in terms of mathematical thinking, a traditional mathematics course presents mathematical thought to students. We'll present them with, here's a theorem, here's a proof, here's some worked examples of its use. It's all tied up neatly with a bow on it, and it teaches you to be able to reproduce that, but it doesn't model mathematical thinking, which is much messier. And so traditional models present mathematical thought, but not mathematical thinking to them. And we just somehow expect them to acquire it automatically. We did, that's why we like maths, but many students don't just acquire it.
Like we teach us with all the scaffolding's been kicked away. We give them the beautiful edifice of mathematics, but none of the how it was built in the first place. And again, that's a very general observation.
And disciplinary appreciation seems to become less of an issue with senior subjects. I guess if a student made it through to third year, they probably like the stuff. But in first year, and especially surfacing subjects where at least our students at Western Sydney are there under duress, and, you know, even if they're not there under duress, they may not be hugely interested in maths. And because of surfacing subjects, you've just got a long list of things you're supposed to get through and a whole lot of skills they're meant to tick off. It's not inspiring for anyone, I don't think. And so that's the observation that, you know, we have time pressures against us, but students are not going to acquire disciplinary appreciation all and think mathematically by magic. And if we're not the people who are building it into our programs, even at the expense of something else, it's just, how's it going to happen?
I guess the other thing is one of the learning outcomes of university is that we want students to become lifelong learners. And somebody, a music colleague of mine, posted a great quote recently about a great educator is someone who, shows you the landscape without pointing it out to you. And I think sometimes in mathematics, we tend to do the opposite. We're saying, look at that blade of grass, look at that blade of grass, look at that blade of grass, oh, look at that tree, look at that. And so we focus so much on that students don't get the big picture. And yet we're supposed to be developing lifelong learners who want to go out and think for themselves.